Good morning, everybody. Let's talk about series. Specifically, we're going to talk about what a series is. We'll also talk about sigma notation, arithmetic and geometric series, which, as you probably guessed, are related to arithmetic and geometric sequences that we learned about last week. First, I'm going to ask you at several points during this presentation to pause it and to try a problem. And this is the first time I'm going to ask you to do that. You are going to find the sum of the positive integers between 1 and 100 without a calculator by yourself in 3 minutes. Is that even possible? Yes. Pause me and try it. Okay, I'm going to assume that you paused me and waited 3 minutes. If not, come on, what are you even doing? Okay, now hopefully you came up with some sort of strategy to do this, and I wish I was there to ask you what your strategy was. Instead, I'm going to tell you what my strategy is. Well, it's not my strategy, but it's probably the same thing at least one of you did. So I'll add these numbers together, 1 plus 2 plus skip a few plus 99 plus 100. Equals something, but what? We'll see. So the key here is that 1 plus 100 is 101, and so is 2 plus 99, and so is 3 plus 98, and 4 plus 97, etc. So you have a whole bunch of pairs of numbers that add up to 101. How many pairs of numbers that add up to 101? Well, I don't want to count them all, but I do know there were 100 numbers to start off with. So if I pair them together, that makes 50 pairs. So that 101 would happen 50 times. Or 50-50. So that is a strategy we can use to add a series of numbers. Here are some examples of series. This one is a finite series. Finite meaning it ends eventually. This one is an infinite series. Infinite or infinite meaning it doesn't end. And a series is basically the exact same thing as a sequence, except instead of just writing the numbers down in some order, you add all of the numbers in that sequence together. And that's what makes it a series. One type of notation that we see connected with series is called sigma notation or summation notation. And it is a quick way to write a sum using notation. We've got this Greek letter sigma, which is sort of like a capital S, S as in a summation. So here's our sigma. On the bottom, we have this variable I, and there's nothing special about the variable I except that it's the first letter of the word index, and an index tells you where something is located. So this index tells us which term in the sequence or series we're talking about. The number on the bottom is the index we're going to start at. The number on the top is the index we're going to end at. And then we add up all of the numbers in between. So we're starting at the third term, ending at the sixth term in this example. And our general term formula is 2i. So for every term, we're going to plug a number into that formula, but the number we plug in for I is going to change. So for the first term, we plug in a 3 for I, and we get 2 times 3, which is 6, just in case you were keeping score at home. For the second term, instead of plugging a 3 in for I, we plug in a 4. So it's 2 times 4. That would be the next term. The next term would be 2 times 5, and then 2 times 6. And because we got to 6, and that is the top number on this summation notation, that's the last term we're going to add together. So we started with the third term, we ended with the sixth term, then we add all those numbers up, and it adds up, in this case, to 36. So there's an example of summation notation with a sigma. Again, every single time we plug in an I value, we use this formula. We just keep changing the number I, starting at the number on the bottom, ending at the number on the top. That's it. Your turn. Pause me and write out each of these series. Write out all the individual terms of this series. Start here, stop there. Try this one too. Pause me, wait a couple minutes. Okay. Hopefully this went great. So every term here is going to be 1 over 2 times something, but the something on the bottom is going to change. So at first it's 1 over 2 times 1, because we're starting at 1. Then the next term would be 1 over 2 times 2. And the next term would be 1 over 2 times 3. I need you to stop that, mouse. Then the next term would be 1 over 2 times 4, and then 1 over 2 times 5. And then the big sigma, the summation, means we add all those together. So plus, plus, plus. And we see what it equals. And it equals something. But the main point was using sigma notation, so I don't really care what it equals. Here, we start with 1, and our formula is just 1. Or it's just I. So the first term is just 1. And then for the second term, when I is 2, we plug in 2 for I, and we just get the number 2. And so forth. Skip a few. And then there's a 99 and then a 100 somewhere. And I just have a feeling that this adds up to 50-50. Just a feeling, a hunch. There is a formula that we can use to find the sum of certain specific types of series. The first type we're going to talk about is a finite arithmetic series. So a very specific kind, finite meaning it ends, and arithmetic meaning it's one of those where you add the same thing each term. And I'm going to give you a reminder of the formula, the general term formula for an arithmetic series. You start with the first term, then you add d, but you add it n minus 1 times. Like that. So that is the general term formula for a specific term. Here, what we're talking about is a summation, the sum of a certain number of terms from this series. So this formula from last week helps us find one specific term. This formula down here by Carl Friedrich Gauss helps us find the sum of a certain number of terms. So here's the idea. You take the first term, that's u sub 1, plus the last term, that's u sub n. You add them together, you make pairs, kind of like we did on this problem, adding up 1 to 100. And when you pair them together, if it is this special type of series, a finite one and an arithmetic one, then you can use this same basic idea. Add the first term plus the last term. They always add up to the same thing. They add up to u1 plus u sub n. They add up to whatever they add up to. And how many terms are there? The number of terms divided by 2. Sorry, that's how many pairs there are. There are the number of terms divided by 2 pairs. N over 2 pairs. So this formula makes some intuitive sense. The formula on the right doesn't make intuitive sense. It makes logical sense, and I'll show you how. Let's start with this formula right here. N over 2 times u sub 1. But instead of writing u sub n again, we're going to replace u sub n with something that it is equivalent to. And u sub n, for an arithmetic series, is always equivalent to the first term times n minus 1 times d. There's a plus in there. And if I combine my like terms, there are 2 u sub 1s, and I get this formula. And the reason I show you this formula is because both of them are in your formula chart that you get to use on your tests at the end of senior year for this class. Hooray for a formula chart. So I want you to get as familiar with these formulas as you can, and I want you to get familiar with them in the way that they are presented on the formula chart. Side note, if I haven't remembered to post the actual formula chart on your ManageBack, you can Google it. Is there a formula for an infinite arithmetic series? Good question. I guess I could answer the question. Let's imagine that this... I pressed the wrong button. Please hold. Let's go back and look at an example of an infinite arithmetic series, like this one on the right. What does this series add up to? Well, the numbers keep getting bigger and bigger and bigger, and we keep adding them together. It's going to equal infinity, or it's going to add up to infinity. Really, we should say it approaches infinity, but that's more important for the second year of AA. For right now, we can just say there's not a formula for an infinite series. It doesn't add up to a number. It adds up to, could be infinity. It could be negative infinity if the terms are negative. But regardless, there's not a formula for an infinite series. It doesn't add up to a number. But a finite arithmetic series does. So this formula only applies to series that are arithmetic and finite. Before you use either of these formulas, make sure you double check both of those things. Is this a finite series? Check. Is it an arithmetic series? Check. Here's an example. Use sigma notation to represent the sum of the first 199 odd numbers. Well, it's the first 199 odd numbers. So is this a finite series? Yes, it ends. Finite. Check. Is this a arithmetic series? I'm writing with my finger. Is this better or worse? It might be worse. Anyway, is it arithmetic? Check. Okay, so this is a finite arithmetic series. It's arithmetic, sorry, because we're adding 2 each time. 1 plus 3 plus 5 plus 7. Every term gets larger by 2 because they're odd numbers. Plus ... Okay. So we want to use sigma notation to represent this. So there's our big sigma. Now, we know we're adding the first 199 odd numbers. So let's start with the first odd number and then with the 199th odd number. Now, importantly here, if we're adding up the first 199 odd numbers, the 199th odd number is not 199. It's actually going to be a bigger number than that. So we need a way to represent odd numbers, and I'll give you a tip. Let's start with an even number. What's a way to represent an even number with algebra? Well, an even number is a multiple of 2. So 2 times something, like 2 times I, would give you an even number. Okay, well, what if I want an odd number? I could start with an even number and then make a little adjustment. If I go either up 1 or down 1 from an even number, I'm going to put a plus or minus here, I get an odd number. So I'm going to decide either to write this as 2i plus 1 or 2i minus 1. And the way I'm going to decide is by seeing what I want for my first number. So I want my first number to be 1. And if I plug in 1 for I, 2 times 1 is 2. Do I need to add 1 or subtract 1 to get to get 1? I need to subtract 1 because 2 times 1 is 2 minus 1 gives me 1, my first term in the sequence. So I know that starting with I equals 1 will give me 1 as my first term. What is my last term? ... I'm going to need my last term to calculate the sum for part B. So I plug in 199 to the formula. So that's 2 times 199, which is 398 minus 1. So 397. Okay. Now how do I calculate the sum? Well, because this is a finite arithmetic sequence, I'm going to use the sum formula for a finite arithmetic sequence. And that is n over 2. So in this case, n is 199. There are 199 terms divided by 2. That's a 9, not a 4. Times the first term plus the last term. So there are a bunch of pairs. Each pair adds up to 398. Then I plug that in my calculator, and I get something. What? I don't really care. What I care is that we understand how to use this formula and where the numbers go. Some series are geometric. Some geometric series are finite, meaning they end. Some are infinite, meaning they never end. Now, earlier we talked about where the formula for a finite arithmetic series came from. For a finite geometric series, I'm not going to show you that right now. It's not because you're incapable of understanding it. You are. I just don't have time. So here's an example. Find the sum of this geometric series. You might think, oh, I can just add the first and the last term together, but no, it doesn't work like that. This is a different type of series. This is a finite geometric series. So a different kind of series, we have a different formula. Remember, a geometric series has R. So let's decide what R is for this series right here. What would I multiply a 1 by a -1 to get a 4? Well, remember you can just divide consecutive terms. What's 4 divided by -1? It's -4. And that's a good way to calculate R. So R is -4. That's one thing I need for my formula. I also need an N for my formula. So I need to know, okay, what would my N value be? That would give me 16,384. And that's a great question. Oops. So to do that, let's recall what our individual term formula is. It's the first term, -1, times R, -4, to the N minus 1. And because I'm plugging in numbers, what I really should have done here is plug in the number 16,384. Now, you might be tempted to multiply the -1 times the -4. Let me remind you that exponents come before multiplication. So we can't do that. What we could do is divide the -1 over, and we could do that. We could also just try some numbers to get in. I should have come prepared. What is this number? I don't know. You'll get to watch me figure it out myself. Okay, so -4 times what? Or sorry, how many -4s does it take me to get up to 16,384? I could solve this algebraically using a logarithm, but you might not even know what a logarithm is yet. I don't know. So instead, let's just type it in our calculators. So what I'm typing in right now is -1 times -4. I'm going to keep multiplying by -4. So there's once, twice, thrice, 4 times, 5 times, I'm not there yet, 6 times, not there yet, 7 times, I'm there. So n minus 1, this exponent here would have to be a 7, because -1 times -4 to the 7th gave me 16,384. That means n itself is actually equal to 8. So here's my formula. -1 goes in for u1. Sorry, this is the sum of the first 8 terms because n is 8. So -1 goes where the u1 is in the formula. Now there are 2 equivalent versions of this formula. It doesn't matter which one I use. I'll use the one on the left because it doesn't matter. So -4, make sure you put that in parentheses because it has a negative in front of it, to the n, which is to the 8th, minus 1, all over r, which was -4 minus 1, equals, and let's see what it adds up to. Since I have my calculator right here, I'll go ahead and calculate it. Let's do the bottom first. The bottom's -5. Didn't need my calculator for that. Not to brag. Then on top, I have -4 to the 8th, which I'm pretty sure is going to be bigger than 16,000. Let's see. -4 to the 8th. -65,536 times -1, so those negatives are going to cancel out. So 65,536, if I typed it in right, divided by -5. Oh, I forgot to subtract 1. That's why it's not dividing evenly. So make that a 5 instead of a 6. 65,530 5. Pardon me. Let's divide that by -5. And we get negative 13,107. There's an example. Now, we're going to do this next. Let me check the time and see how much time we have left. Do quick pause. Oh. Let's see. How long have we been recording? This is a good use of our time. Me checking how long we've been recording. 27 minutes. Okay. So I think we can do this and then another couple of problems afterwards. All right. Now I need to go back to the screen that I'm sharing. It's this one. It's going great. Hey, how's it going? You just won the lottery. Way to go. So the way the lottery works, just in case you aren't sure, at least in the United States, in some states, it's different in other places, is you buy a ticket, and if you get the winning ticket, you get money. And usually the money that is raised by this goes to help like schools and things like that. But anyway, I digress. When you win, you might have some different options for how you are given the money. And I'm giving you two options here. You can either take option A or option B. Now, I will give you the hint that one of these options is an arithmetic series, and one of them is a geometric series. Which one is which? Well, you'll have to decide that. So I want you to take about 5 minutes, grab your calculator, do some calculations, use some of the formulas from earlier in this lesson, and try and decide how much money you're going to get from each of these options and which one you would choose. And after about 5 minutes, I want the class to take about 5 more minutes to share their thoughts and to talk about it. And then you can unpause me and go. Okay, wow. That was a great discussion, class. I'm interested to hear which options you would have picked. Sadly, I can't. But I'll at least share some math with you. And in that way, we all are winners. So option A is the geometric sequence because you're doubling the payout each day or each year, sorry. And so to find the total payout, we need first off what's arriving on the sorry, let me back up. We need to use the right formula. We need what's arriving on the first day. So for geometric series, we got 1, and then we do the r to the n minus 1, that formula. So r is 2, that's what we're multiplying by. N is 31, obviously. I don't know why you would say 30. Actually, I do, because the first time I tried this, I did 30, but then I thought about it. You're getting paid today, and then 1 year from now, you're getting a second payment. And 2 years from now, you're getting a third payment. So 30 years from now, you're getting your 31st payment. So it's actually 31 payments that you'll be getting. And then we put that over r minus 1. So 2 minus 1, which is 1. And then you type that in your calculator, and it's like, I don't know, 5 billion something. You all already calculated it, so you can fact check me. Option B is arithmetic because we're adding $1 each year. So 100,000 plus 100,001 euro plus 100,002 euros. So I'd say option B, still pretty good, but it's not going to make you $5 billion. So to put that in the arithmetic formula, we are going to take n divided by 2, and of course it's 31 again, times 100,000 plus 100,030. And you add that together, and it's going to be, I don't know, like 3 million. Pretty good. Not as good as 5 billion. But you know what? I'd take it. Plus, 30 years from now, I'm pretty old. I might not even be alive. Now, what about the sum of an infinite geometric series? So infinite means the n value, the number of terms in the sequence. It doesn't equal infinity because infinity is not a number. You can't equal infinity, but you can approach infinity. So n is going to get bigger and 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 bigger, and it never stops. And what happens depends on how big your R value is. If your R value is equal to 1, first off, that would be a really boring sequence. Let's say my R value is 1. I start with 4. Oh, sorry, a series I'm adding. And then I multiply by 1 and I get 4 again. And then I multiply by 1 and I get 4 again, etc., etc., etc. Now, this is going to be a really boring series. It's also going to add up to infinity, because if you keep adding 4 together, or any number, it's going to add up forever and add up to infinity. So for an infinite geometric series, we really don't have a formula to use because it doesn't add up to anything in particular. It diverges, we would say. It just goes up and up and up and up and up, or down and down and down if it's negative numbers. What if R is bigger than 1? Okay, well, let's take these numbers and instead of keeping it as 4, let's double it each time. 4 plus 8 plus 16 plus dot, 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 dot. And you can probably tell this is going towards infinity, only faster. So we also don't have a formula for an infinite geometric series where R is bigger than 1. But there's a third option. What if R is smaller than 1? So what if we cut this in half each time? Now we're still adding a bunch, but notice what we're adding gets smaller and smaller and smaller and smaller and smaller. And keep in mind, this is essentially like exponential growth or decay. So it happens fast. So what do you think? Is it going to add up to something? Is it going to approach infinity? And we're still adding forever. But the things we're adding are also getting smaller and smaller and smaller. They're getting infinitely small. So it turns out that with a little bit of investigation over here, we can actually figure this out. So let's say that R was, for example, I'll say 0.1. Just a number smaller than 1. And let's raise that to a really big power, like, I don't know, 1,000. What does 0.1 to the 1,000 mean? Well, that would be a 0 followed by a decimal place, followed by a whole bunch more zeros. How many zeros? I'd say about 1,000. and then a 1. So 0.000000000000001. Or basically, this is approaching 0. As the exponent gets bigger, you just keep adding more and more zeros. So this is approaching 0. And 1 minus 0 is 1. And so that simplifies the top. And this term in parentheses basically goes away. And you get just this right here. So this only works with r less than 1. And really, because r can be negative as well, it's with an absolute value for r being less than 1. So somewhere in between -1 and 1. Okay. We're going to try these. It says independent practice. Let's just try them together, because then you can do your own independent practice. So find the sum for the infinite series. This is a geometric series where you're multiplying by 1/5. So the sum would be, it's infinite, so we want to make sure we use the right formula. That's the first term over 1 minus r. Here, r is 1/5. So the first term over 1 minus r. And that would simplify, so that's 4/5. 2 divided by 4/5. Copy dot flip. I guess I'll write out some math. 2 divided by 4/5 is the same as 2 times 5/4. A little math trick. Multiply by the reciprocal, which is 10/4, or 2.5. Okay, I'm going to check the time. I feel like I'm probably, running up on the end of class here, depending on how lengthy your discussion was. So you've got a whole bunch of practice problems on ManageBack. Please don't do them all. They are there for you to use. I would say, go through like the first 3 or 4 pages of the arithmetic and the geometric, and try to do as many of those on the first 3 to 4 pages as you can. You also have the answers posted as well, if I remembered to post them. And do those, check those out first, and then maybe go deeper into the packet and try 1 or 2 questions and see how you feel about it. If you feel bad about it, you might need to try more. If you feel great about it, you might need to try more, just in case. Now, if you have your next class tomorrow, you might not have time to do that much between now and then. That's okay. We'll have some time to work in the next class, or at least the next class period. So I'm going to sign off for now. Go find your independent practice and get to work.